We're going to start by looking at a molecular example of dynamic equilibrium that's related to solubility. Our learning goals for this video will be to develop a microscopic picture of the solvation process and then to distinguish between soluble and insoluble solutes. One observation I'd like to make is that you've probably tried to dissolve some sugar into iced tea or into coffee or some other kind of drink, and there are some observations you've probably had in doing that. First of all, you've probably noticed that you can't dissolve a whole bunch of sugar in there. There's a limit to how much you can dissolve into the tea. You may have also noticed that you can dissolve more sugar into hot tea than you can into iced tea, so heat somehow helps to increase solubility. Finally, we know that adding water would also help us dissolve more sugar, so if we can't get all the sugar we want in there, we could always add water and dissolve more. So there are several things we can infer from this. One, very clearly, water has a finite capacity to dissolve sugar. We can't dissolve as much as we want. We can only dissolve a certain amount and then it stops dissolving. That's even for something that is soluble like sugar. We also see that heat aids the solvation process, and one of the things we know about heat is that it causes molecules to move faster. So we haven't described yet why that helps the solvation process, but it's something to tuck away so that as we think about this more deeply and learn about the microscopic picture, we might get some insight into this. So we're going to presume that there is a solubility equilibrium. And in a sense, that means that there has to be both dissolved solute particles and solute particles that are part of the solid that hasn't dissolved yet. So this leads to a certain kind of microscopic picture. And again, we're looking for features that indicate that this is a dynamic equilibrium. So we need smaller mobile units. And in this case, those smaller mobile units are the solute molecules themselves. So here's a cartoon that shows something about salt dissolving in water. And we can see that over time, the water molecules are going and they're picking off one ion at a time and surrounding it into a solvent shell. And that's the process of dissolving that's taking place. We know that it's a closed system because typically when we're dissolving something, we've added a finite amount of solute, we have a finite amount of solvent, and we're not adding any more to it, so it's a closed system. What we haven't established yet is reversible dynamics, although I will say that we're pretty confident that this does happen in the case of solubility and solvation. So let's talk about reversible solvation. So there are two states of solvation. There's the state where you have solute that's part of the solid sample, and you also have solute that's part of the solvated solute molecules. So it's not the situation where these just dissolve and then you have dissolved molecules and solid molecules and they don't interchange. In fact, there is an interchange that's going on. So for example, in the case of lead sulfide, which is technically an insoluble compound, if I throw some lead sulfide into water, I am going to generate some ions, some lead +2 and some sulfide -2 that are in aqueous solution as ions. They're solvated as the individual ions. And all of these species, the solid lead sulfide and the two ions of lead 2+ and sulfide 2-, all coexist in solution. Now the amount of solvent is what really determines the capacity for dissolving. So if I wanted to dissolve all of the lead sulfide that I happen to have handy, I could probably do so by increasing the amount of solvent until I have an immense amount of that. But I know that whenever I get above a maximum concentration, the solute is going to recrystallize. Okay, this is an observation one can make. So what that tells us is something very interesting. It says that basically every solute, so in this case lead sulfide or sodium chloride or sugar, whatever it may be, has a certain characteristic maximum frequency when it's in solution. If it exceeds that maximum maximum concentration, if it exceeds that maximum concentration, it's then going to recrystallize and form a solid again. Otherwise, it will remain in solution. So this is really what distinguishes soluble and insoluble compounds from one another, is really what is their maximum concentration that they can achieve when they encounter the solvent.